Okay, this last video for Unit 1 is should be a pretty short one. It's just the tail end of some information about antigen and antibody reactions and then how we grade those agglutination reactions. So there are a few different things that can influence that binding between the antigen and the antibody. So goodness of fit and complementary nature of the antibody contributes to the strength and the rate of that reaction. So the size, the shape, and the charge determine the antigen's binding to its complementary antibody. So again, think about that as kind of like a lock and key mechanism. If you don't have the key that is made for that specific lock, then it's not going to open the door. So these antibodies are specific to their antigens. So affinity is the term that refers to the strength of the binding between that single antibody and the epitope of the antigen. Avidity refers to the overall strength of that reaction between several epitopes and antibodies. Centrifugation is one thing that can affect that reaction. So if the sample was centrifuged either not long enough or for too long, it can not lead to optimal reactions. The time, the temperature, pH of the incubation process, electrical charge, so that can be referred to as either by a couple different terms, the dielectric constant, the zeta potential, and the plane of shear. So in here, again, just a visual representation of that lock and key mechanism. So you can see that the portion of the antibody right here, which represents this, is made to fit this antigen, whereas this one is not. So you're not going to get a good or optimal antigen-antibody binding. Okay, some characteristics associated with red cell antigen antibody reactions. So red cell antigens are part of the red cell membrane, or they protrude from the cell membrane. Red cell antibodies are molecules that are present in the plasma or the serum. So previously we've been talking about antigens and how they kind of relate, antigens and antibodies and how they relate to immunity. So now we're talking about how they relate to blood banking and how we're testing blood cell antigens to antibodies that are in a patient's plasma or serum. So and then you've got a picture there of here's your antibodies, those little Y shapes. They're going to be present. So this is a blood sample that's been centrifuged. It's been spun down. All your red cells are on the bottom here. So that's where your antigens in your sample come from. They're on the red cell. And then the top portion of that centrifuged sample is either the serum or the plasma. So that's where the antibodies will be. And then you've got that buffy coat in the middle there. Okay, red cell antigens protrude from the surface of the red cell membrane. They can interact with antibody molecules, which results in agglutination reactions. So agglutination that involves red cells is specifically referred to as hemagglutination. The blood bank department of the lab performs testing to determine if a patient's blood type, so we determine the patient's blood type using those hemagglutination reactions. So you guys just kind of touched the surface of this in intro when you were doing some blood typing. So routine testing will identify those ABO antigens from the ABO blood group system and the D antigens from the RH blood group system. And the identification of those antigens is what determines the patient's blood type. Okay, red cell antibodies. So the most significant immunoglobulins that we have to take into account in transfusion medicine or in blood bank are the IgG and the IgM antibodies. The most clinically important antibodies are going to react at room temperature, which is around 37 degrees Celsius. They're IgG, and they can cause immune destruction of transfused red cells that possess the corresponding antigen. So that's why we have to make sure that blood that we transfuse to a patient is compatible, that we're not introducing them to any foreign antigens that they could have an antibody reaction to. So the destruction of the red cells can cause transfusion reactions, anemia, hemolytic disease of the fetus and newborn, which is a condition caused by destruction of fetal or neonatal red cells by maternal antibodies. An antibody that actually lyses a cell is referred to as a hemolysin. Your IgM antibodies are going to react best at room temperature, so that can be defined as usually somewhere around 20 to 22 degrees, sometimes a lower temperature. Your IgM antibodies are usually not going to be implicated in destruction of transfused red cells. ABO antigens are the exception to this rule, though. Antibodies to ABO antigens are IgM antibodies, and they react in vitro at room temperature and in vivo at body temperature. So transfusing the wrong ABO blood group antigen would activate the complement system, and cause hemolysis of those transfused cells. Okay, immunohematology, you've got in vivo antigen antibody reactions. So that means a reaction within the body. This can happen in transfusion or pregnancy. So the patient is exposed to foreign antigens on red cells, white cells, or platelets. So the patient's immune system can become activated. It'll start to produce antibodies to those foreign antigens that they've been exposed to through either transfusion or pregnancy. These are called allo antibodies because it's antibodies that the patient's going to build to a foreign substance or to something that's not self. So these are naturally occurring antibodies. Allo antibodies can occur during transfusion, so it introduces the body to foreign antigens. Your body builds antibodies in response to those foreign antigens. It can occur during pregnancy. Sorry, I got behind again. It can occur during pregnancy. I wasn't behind. Where fetal blood cells can enter maternal blood circulation at the time of delivery. So allo antibody production can result from red cell, white cell, or platelet antigens from the fetus. Because of this, the moms get screened during their first trimester and can be treated to help prevent issues like anemia and very high, which would occur in the mom, or very high bilirubin levels in the baby. So the antibody screen, the test that we perform in blood bank called the antibody screen, it gets done before transfusion, and we're doing that to screen for the presence of those allo antibodies. So we're trying to determine, has the patient ever been exposed to foreign antigens, either through transfusion or pregnancy, and has that caused the allo antibodies to form. So if allo antibodies are detected during that antibody screen, we have to determine the identification of the antibody, and any donor units that we're going to give to the patient for transfusion have to be lacking the red cell antigen that the patient has the antibody for. Because if we're providing the lock and key, so the patient has the lock, we're providing the key through that process of blood transfusion, then we're going to have a reaction, an agglutination reaction. If the patient were to encounter these antibodies, so say for instance, if the transfused blood units were not screened which can happen in cases of emergency release. Extravascular destruction of those cells by the spleen and the liver would occur, as well as intravascular hemolysis of the red cells. Okay, so in vitro antigen antibody reaction. So this is a reaction in an artificial environment. So that's like your test tube, like what we're doing in the lab. It's detected by visible agglutination or hemolysis. Either one of those is considered a positive result. It indicates that an antigen antibody immune complex was formed and the specificity of the antibody matched the antigen in the test system. So hemagglutination occurs in 2 stages. We've got sensitization and then the lattice formation step. So in the sensitization step, you've got a sensitized cell. So what's happened is there was binding of either antibody or complement components to a red cell. So some factors that can influence that sensitization stage: the serum to cell ratio. So if we increase the amount of serum in the tube, it increases the concentration of the antibodies that are available to bind to those red cell antigens. The temperature of the reaction. So antibodies get classified as either cold or warm, depending on their optimal reaction temperatures. So IgG antibodies react best at 37 degrees Celsius or body temperature, so they are considered warm antibodies. IgM antibodies react better at room temperature, so they're referred to as cold antibodies. The time of the incubation. So we have to allow adequate time for that antigen and antibody to attain equilibrium. That time, that adequate incubation time can vary depending on the test procedure, depending on the reagents that you use in the procedure. So some examples could be the immediate spin portion of the testing, possibly also after a specific time. So we're gonna, immediate spin's done at room temperature, or it could be at 37 degrees. So if we increase the incubation time, it could help with weak antibody reactions. So if we do that immediate spin, which means there has not been an incubation step that has occurred yet, and we see what we think might be an antibody reaction trying to form, if we incubate it and then look for that agglutination reaction again, it might be stronger. The pH can help. So the optimal pH for hemagglutination to occur is around 6.5 to 7. And then the ionic strength of some of the reagents. So low ionic strength reagents help to increase the rate of the antibody uptake onto the cells. So it can also help to reduce incubation time. Okay, and then the second stage is called lattice formation stage. So after those red cells have been sensitized with the antibody molecules, you'll have random collisions that occur between those antibody-coated red cells. So those collisions are necessary to develop cross linkages. So they have to kind of bump into each other so that they can then kind of link and hold on to one another. So that the result of that is visualization of the red cells that are clumping together, which is known as agglutination. So those visual agglutinates form when red cells are near, and they promote the lattice formation of the antibody binding sites to the antigenic determinant on those nearby red cells. Okay, the zeta potential is a term that refers to the force of the repulsion between the red cells in saline, or the charge of the red cells at the plane of shear. So it can exert an influence on that agglutination reaction. Because of the larger size and the pentametric shape, multivalent properties, the IgM antibody molecules are going to react easier. So in contrast, your IgG antibody molecules are smaller. they're less able to span that distance between the adjacent red cells. So the IgG molecules may attach, but you may not have that visual agglutination. Then the zone of equivalence. So when the number of the binding sites of your multivalent antigen antibodies are about equal, so that's what that zone of equivalence means. You've got an approximately equivalent number of binding sites between your antigen and your antibody. So blood bank testing is designed to obtain those reactions, within that zone of equivalence. So you've got commercial antibody preparations get diluted to optimal antibody concentrations so that we can test them. And then red cell preparations are diluted to between a 2 to 5% suspension in saline and that's considered an optimal antigen concentration. So when our reactions in the lab are outside of that zone of equivalence, you can have what's either called prozone or post zone. So prozone is where you have an excess of your antibody, so it can cause a false negative reaction. Post zone is where you have an excess of your antigen that can cause a false negative reaction. So either way, either prozone or post zone, both will cause a false negative reaction because you're not getting that reactivity within the zone of equivalence. And here's just a visual representation of that, where you've got too much antibody. So you see your little Y shapes here, too much antibody, not enough antigen, or the opposite. And then here's our Goldilocks reaction there. Okay, the last little bit that we're going to talk about in this video are, oh wait, I think that was one thing I forgot to mention. Yeah, so centrifugation is one of the things that can play a role in either prozone or post zone. So the time and the speed of the centrifugation are important factors for detection of those agglutinated red cells. So it helps facilitate that formation of your latticed network because it forces the red cells closer together in the test environment. So either over centrifugation or under centrifugation, too high or too low of a speed can cause either false positive or false negative reactions also. Okay, so then the last little bit here, grading agglutination reactions. So our antigen antibody reactions are detected with red cell agglutination. So we know that an antigen antibody reaction has occurred because we can visually see that agglutination reaction. So reactions may be performed in test tubes, in microplate wells, in microtubes filled with gel particles. Those reactions are measured qualitatively. So the reading and the grading is very subjective. So it depends on who's performing the testing, who is reading and resulting the testing. So there's a conventional grading system for tube testing that uses a 0 to 4+ scale. So a lot of times if your microplate wells or microtubes in the gel particles, those are different types of testing that can be performed in automated instruments. A lot of times the instrument's going to grade that agglutination reaction for you, but if you're doing tube testing, you're going to be grading it yourself. So grading the hemagglutination, so a 4+ reaction would be referred to as, if you're seeing a red cell button, so that's that solid button, it's a solid agglutinant. There's no questioning that reaction. 3+ is several large agglutinants with a clear background. 2+, you've got some medium-sized agglutinants with a clear background. 1+, you might see some medium and small-sized agglutinants. The background could be turbid due to a lot of free red cells. A 0 or a negative means that there are not any visible agglutinated red cells. So red cells observed flowing off of the red cell button during the process of grading. And then hemolysis red cell button is a lot of times smaller. It can be pinkish to reddish, supernatant after centrifugation. Excuse me. And then there is another video in Moodle, a YouTube video called Immunology Review. I would recommend taking a look at that video now. But that is the end of the lecture videos for Unit 1.